The topic is not new, but we know the technology is fast. So many technical development in the area of solar water pumping using various kind of motor drives like DC motor drive, induction motor drive, permanent magnet synchronous motor drive, brushless DC motor drives, and other. Here I have used a brushless DC motor drive for water pumping using solar photovoltaic energy. So reason behind using this brushless DC motor drive is the high efficiency of this BLDC motor, because we know the efficiency of solar panel is very less, around 20% only. So how we can get maximum output from the solar panel? By using high efficiency power electronics converter and by using high efficiency motor drive. So that's why I have employed a brushless DC motor drive in solar water pumping system. So before going through the technical contribution on this topic, I would like to highlight the development of water pumping in our country, in India. How the government of India is promoting the installation of solar water pumping across the country. You can see this data, about 19 times higher solar pumps installed between 2014 to 2019. That is 2.25 lakh versus up to 2014. So you can see up to 2014, only 11,626 solar pumps were installed throughout the country. Only 11,626 up to 2014. Now, in between 2014 to 2019, means within 5 years only, 2.25 lakh of solar pumps have been installed in the country, in various states of India. That is actually 19 times higher than whatever installed before 2014. So this shows the interest of Government of India, interest of Ministry of New and Renewable Energy in the installation of solar water pumping because of various advantages of this scheme. So as I said, Government of India is promoting the installation of water pump through various schemes. Government of India has launched various schemes for the middle class farmers of India, so that the middle class farmers of India can afford the installation of solar pump. One of these schemes is called PM Kusum. PM Kusum is Pradhan Mantri Kisan Urja Suraksha Evam Utthan Mahabhiyan. So through this scheme, 1,81,000 irrigation in 3 years has been installed across the country. So you can see this table. This table shows the number of solar pumps installed under this scheme. So as on October 31st, 2020, 1,81,521 solar pumps have been installed. 2020, you can see the Chhattisgarh is leading among the other states. In Chhattisgarh, you can see 60,000. This is the Chhattisgarh. 60,430 solar pumps have been installed under this scheme. Right? There are so many other schemes like Saur Sujla Yojana. Through Saur Sujla Yojana, around 51,000 of solar pumps have been installed in Chhattisgarh state. Other schemes are like Jawaharlal Nehru National Solar Mission. So there are so many schemes through which Government of India is promoting the installation of solar water pumps for the farmers, basically for the irrigation. Okay, now we will see which type of motors can be used for the water pumping, especially in solar photovoltaic system, and which motor will be more suitable for this application. So starting from very basic motor, very conventional motors like DC motor, then induction motor, then PMSM, that is permanent magnet synchronous motor, BLDC motor, that is brushless DC motor, then SRM is switched reluctance motor, then SYRM, okay. So we will compare these various types of motor. So starting from DC motor is conventional DC motor with commutator and brushes. So when we use this DC motor, we can directly connect this motor across the PV panel because PV panel gives DC voltage. So DC motor also needs DC input voltage. So DC motor can directly be connected across the solar panel. So that was one of the advantage with DC motor for solar water pumping system. So one conversion stage is avoided. One conversion stage means VSI. VSI is voltage source inverter. So we don't need any inverter if we use simple DC motor for water pumping with solar panel. But this is not preferred because of frequent maintenance required. It has a mechanical commutator, it has carbon brushes which need frequent maintenance. So that's why nowadays we are moving towards the high efficiency motor which needs especially DC motor and induction motors were being used for solar water pumping system. Now next is induction motor. The induction motor is more reliable and maintenance free as compared to the DC motor. It is suitable for hazardous and contaminated areas that we know. So only problem with this induction motor is it needs complex control system. For the speed control of induction motor, we need costly control system and complex control system. Now, nowadays we have special machines, or we can say advanced machines. Why these are called special machines? Because these are specially designed for special application to get highest or maximum efficiency from the motor and DC motor. But still we are using this special machines. Am I audible?
Yes, sir.
Okay. Okay. So these special machines have very high efficiency. If I talk about this PMSM, that is permanent magnet synchronous motor, and BLDC motor, that is brushless DC motor, efficiency of these motors are always more than 90%. So we can use this motor to get maximum output from the solar panel because solar panel efficiency is just 20% maximum. So if I use this PMSM or BLDC motor in place of induction motor, then I can get maximum water delivery from the same panel. So if I talk about PMSM, that is permanent magnet synchronous motor, so it is useful in submersible installation because of its higher efficiency as compared to the induction. Efficiency generally we know it is around 80%. Induction motor has electromagnetic excitation system, and when there is electromagnetic excitation system, there will be electromagnetic excitation loss. Excitation loss will be there. That's why efficiency of induction motor is just around 80%. But when we use permanent magnet synchronous motor, there is a permanent magnet in the rotor of synchronous motor. That is called permanent magnet synchronous motor. Means there will be a permanent magnet excitation system. So when there is permanent magnet excitation system, the excitation loss will be completely zero. There will be no excitation loss in the motor. That's why the efficiency of these permanent magnet machines are higher as compared to the induction motor. Even at lower voltage, when we operate the induction motor at lower voltage, efficiency gets decreased. But in case of permanent magnet motors, even with it gives very good efficiency because of zero excitation loss. So that's why permanent magnet synchronous motor is better than induction motor in terms of efficiency and performance. But in terms of cost, obviously PMSM is costlier than the induction motor. So it is better for global efficiency optimization of SPV fed water pumping. So now Ministry of New and Renewable Energy, that is MNRE, is encouraging the use of the high efficiency motors like PMSM and BLDC motor for solar water pumping. Previously, the MNRE was recommending only DC motor and induction motor, but nowadays that ministry is recommending high efficiency motor so that we can extract maximum power, we can extract maximum output from the solar panel. Now coming to BLDC motor, that is brushless DC motor. So it is called brushless because it has no carbon brushes. It doesn't need carbon brushes like a conventional DC motor. And it needs commutation, but its commutation is through the electronic system. Commutation is not a mechanical commutation. It has electronic commutation. And we know efficiency of electronic system is far better than that of mechanical system. So electronic commutation means it gives good efficiency. That's why BLDC motor has very good efficiency in comparison with the conventional DC motor. Conventional DC motor efficiency is not more than 75%, maximum 75% because of carbon brushes and mechanical commutation. But efficiency of this brushless DC motor is always more than 90%, even with the low input voltage. And it is called DC motor. Why it is called a DC motor? Brushless DC motor, because its characteristic like torque speed characteristic or torque current characteristic is almost similar to the conventional DC motor. That's why it is called brushless DC motor. Otherwise, it is AC motor only. It needs three-phase input supply. Three-phase supply it needs. But it is called brushless DC motor just because of the similarity in the characteristic. Otherwise, it may be confusing. It is actually an AC motor. It needs three-phase input voltage. It doesn't need actually a DC voltage. It needs three-phase input voltage. It is actually AC motor, but it is called DC motor because of the characteristic. So this is also a permanent magnet motor. Okay, in the rotor of BLDC motor also there is permanent magnet for the excitation. So if we compare this brushless DC motor with permanent magnet synchronous motor, both this PMSM and BLDC are synchronous motor only. Synchronous motor means this can run at synchronous. Now, what is the difference between this PMSM and BLDC? Is we can see the BLDC motor has 15% higher power density than PMSM. So its power density is 15%. Its size.
Hello, sir.
Yes.
Sir, voice is breaking in between the.
Okay, voice is not clear.
Now it's clear, sir. Now sometimes it is breaking in between.
Okay.
Sir, voice is clear. It's his internet problems.
Internet problem.
Okay, let's see. Yes.
Is there any connection problem from my side?
No, sir. Now it's okay, sir.
No, sir. It's fine, sir. It's very clear.
Yes.
Okay. Please interrupt me if there is any problem. Okay.
Yes, sir.
Sir, can I ask question at the last or between?
No, sure. We can discuss anytime. Please.
Okay, sir. I will make a note, sir, because at the last I will ask.
Okay.
Hello.
Otherwise, you can
sir.
ask anytime. We can discuss anytime in between the lecture.
Yes,
Okay.
sir. Participants can. I think that if they ask in between also, it will be more interactive and it will be good.
Yes. You can interrupt me anytime. It may be actually an interacting session.
Yes, sir. Sir, sir, we actually says that BLDC is the AC we give like that. But sir, it is like the input for the voltage source inverter is a DC, and every time we are feeding to the BLDC as a 6-step commutation. In that case, the switches are switching on and switching off. In that case, only positive voltage is applied to the stator, and rest of the time it is applying 0 voltage. but there is no negative we are applying to the stator. So in that case, I would like to know how we can call it as the AC supply to the BLDC.
Actually, basically, if we see the BLDC is a three-phase machine, three-phase motor. It needs, we know the input of the voltage source inverter is DC voltage, but at the output of inverter we are getting AC, and final input to the motor is AC only, three-phase AC only. So it is actually a little bit confusing. Somebody may be confused that why we are calling it a DC motor, because final input is three-phase input. So three-phase means it is AC. How three-phase can be DC? Okay, and one can say that yes, it is DC motor because input of the inverter is DC. So he is also correct if he say that it is a DC motor. But if we ignore the inverter, if we talk about the motor only, let's say only the BLDC motor, we are not counting the inverter, then it is an AC motor only because it needs three-phase voltage. So how we can say that it is a DC motor? So both are actually correct, but this is just a point of understanding, how we can understand actually. So that's why I said that this is actually an AC motor because it needs three-phase input. But we can call it a DC motor because if we draw the torque speed characteristics or torque current characteristics, it will be exactly same as the conventional DC motor. That's why it is actually called a DC motor, brushless DC motor. This is not because of the inverter input voltage. Inverter input voltage is DC. That's why somebody can say that input of brushless DC motor is DC, but somebody can also say that input is three-phase. So that's why it is an AC motor. So actually both are correct. As I said, that this is just a point of understanding, how we can understand, right?
Yeah, yes, sir. But we are giving supply to inverter is DC, but
Yes.
the output of inverter is not AC, no, sir. Because based on the position of the sensor, we are energizing the two phases of the stator. While energizing the phases of stator, we are applying only positive voltage to those stators, stator two windings, and we are not giving negative portion of the supply to the stators. If we give positive and negative supply to the stators, the resultant will be the field production resultant. If it happens, then we can tell it as a AC supply we are giving to stator. But for stator, we are always giving, we are every time we are chopping the DC supply to the stator for two phases with respect with the help of voltage source inverter. We are giving the switch pattern like that. So we are not, nowhere we are giving negative portion of the supply to the stator. That's why I'm getting confused whether it is a AC motor or DC motor.
At a time, actually two phases conduct, right? At a time, two phases will conduct. So in one phase current will enter and from the another phase current will exit. So in one phase current will be positive, in another phase current will be negative. Okay, if you look into the voltage applied across the phases of this BLDC motor, that will be a trapezoidal voltage, right? So trapezoidal voltage means it is AC voltage. It is fluctuating between positive and negative. So it is AC. How it can be DC? It is fluctuating between positive and negative. If you see the waveform, if you see the voltage input, right? You see this voltage, this is input voltage of BLDC motor. This is actually trapezoidal. Voltage. So it is, we can say it is an AC motor. But because input voltage is AC, now input voltage is not DC.
Yes, sir, but the back EMF is AC, sir, because the rotor rotates in a 360 degrees, a positive, negative cycle comes out from the back EMF, but whereas the positive and zero, right, sir?
In the stator.
Sir, because other voltage source inverter ka functionality is like based on the position of the rotor, and we determine what two phases to be given supply, so that those two phases will give poles for the rotation of the rotor. So this is the back EMF what it is produced. It will be AC only, sir, but the supply what we are giving to stator is positive and zero only.
supply we are giving to the stator winding. Stator winding means that may be across phase A and phase B. That is actually stator winding. So across phase A and phase B, we are applying the this trapezoidal input voltage only. We are not providing positive, and you are saying that positive and zero. That is actually plus positive and zero is actually the Hall signal is positive and zero, right? Means high and low.
Yes,
But
sir.
ultimately, at the input of stator means the phase windings are the stator winding. So across the phase windings, we are applying trapezoidal voltage only through the commutation, through the 6-step commutation. So this kind of voltage, which is shown in this result, this kind of voltage is applied across the stator winding only. This first waveform, you can see this is written as EAN. That is this is the back EMF only between the phase and neutral, phase A and neutral, EAN. So this AC is actually applied only in the stator winding also. Stator
Okay.
winding.
Yes. Okay.
We can see some more results later on,
Yes, sure, sir. Sure.
so that it may be cleared.
Yes, sir. Yes, sir.
Okay, so as I said, reason behind using this brushless DC motor is only its high efficiency. Otherwise, there are some drawbacks of this BLDC motor also. Drawbacks are like it is costly. Why it is costly? Because it needs permanent magnets, and we don't have permanent magnets in India. These permanent magnets are generally imported from China. That's why the cost of permanent magnets are higher in India. And that's why in India, we are actually unable to design, we are unable to manufacture this brushless DC motor. That's why cost is higher. Even for electric vehicles, there are so many rickshaws in India, but nobody is actually manufacturing BLDC motor in India. All the BLDC motors, these low cost BLDC motors are imported from China only, because China has permanent magnets. In India, we don't have permanent magnets. So that's why the cost of BLDC motors are higher. We can save, means we can increase the output of the solar panel by using this high efficiency motor. That is the reason only. It is written here. We can compare this BLDC motor with the PMSM. Efficiency wise, both this PMSM and BLDC motor are same. Difference is PMSM motor, this is also an AC motor. PMSM, just like BLDC motor, input of PMSM is also DC only. Okay, input of PMSM is also DC. Okay, there will be some DC input voltage, then there will be a voltage source inverter. At the output of voltage source inverter, there will be PMSM. So initially input voltage will be DC, output of inverter will be AC voltage, sinusoidal AC voltage, and that sinusoidal AC voltage will be fed to the stator winding of PMSM. In case of BLDC motor, that voltage will not be sinusoidal, that voltage will be trapezoidal. That is the difference. In case of PMSM, voltage will be sinusoidal. In case of BLDC, voltage will be trapezoidal. Now, size wise, if you compare the size of PMSM and BLDC for the same power output, size of BLDC motor will be 15% less for the same power output. That's why it is written here 15% higher power density than PMSM. Power density is higher means size of BLDC motor will be 15% less. Now it has very high efficiency because of permanent magnet. Permanent magnet has no excitation loss. Long life. Long life means why it has long life? Because it has no carbon brush, so it is maintenance free. It has no mechanical commutator. That's why it has long life. High reliability, low radio frequency interference, no maintenance. These are the advantages, merits of BLDC motor. That's why it is suitable. It is most suitable candidate for solar water pumping system. There are other special machines like SRM, that is switched reluctance motor. So this switched reluctance motor and SYRM means synchronous reluctance motor. These motors are actually in research phase, we can say, you cannot find any practical application of these motors in water pumping system, solar water pumping system. Okay, we can find the application of DC motor, induction motor, BLDC motor in solar water pumping. But this SRM find any practical application. But these motors can also be a good candidate for solar water pumping because this motor also has very good efficiency. So nowadays, as I said that these motors are in research phase, these are suffering from high torque ripple SRM. SRM has very high torque ripple and acoustic noise problems. It has not received much attention for PV air-fed water pump till now. Similarly, in SYRM, synchronous reluctance motor, some attempts in the area of PV air-fed water pump using SYRM has been made. Some attempts are made just in research papers or in publication. Okay, I have not seen any practical application of this motor in solar water pump. These are in publication, these are in research phase. That's why this is not well proven. So these are the list of motors which can be used for solar water pumping system. So in this presentation, I have used a brushless DC motor and I have designed a controller for this motor for water pumping system, solar water pumping system. So there may be a number of topologies using this brushless DC motor for water pumping system. You can see solar PV fed BLDC motor driven water pumping system can be classified into position sensor based BLDC motor drive and position sensorless based BLDC motor drive. Means we know there are 3 Hall position sensors in BLDC motor to sense the actual position of the rotor. So we can control the speed of BLDC motor through that position sensor, or we can
Hello. Hello.
Sir, it's completely blank, sir. May I know? Like,
So he will join soon.
thank you, sir.
is it visible now?
Yes, sir.
sir.
It's
It,
visible, sir.
Sir, if net speed is slow, then you can mute stop your video, sir, so that it can, I think that
Okay,
the problem.
okay,
Yes, sir.
that will be better. Okay.
Yes, sir.
Okay, is it visible?
Yes, sir.
Yes, sir.
Slide is moving.
Yes, sir. Yes, sir.
Okay, thank you, thank you.
So please start from the comparison point of view, because at that point your voice is somewhat not audible. So please start from here only. Yes, sir. From this slide.
Okay.
Okay. Thank you, sir. And so one question from participant is that in a grid connected mode of PV fed BLDC motor, the AC power from grid has to transform into DC, or else we can rectify it to the motor.
Okay, so I have the answer of this question in the next slide. So you can
Okay,
go ahead.
okay, sir.
Okay,
Yes, sir.
so
Yes, sure.
right. So we were comparing this brushless DC motors with the other special machines like SRM and SYRM. So SRM, that is switched reluctance motor, synchronous reluctance motor. This we have no practical application of this motor nowadays in solar water pumping system, but these motors can.
Hello, sir. Hello. Hello.
Okay, am I audible?
Yes, sir.
Okay. Sorry for the interruption. Actually, now I have connected through mobile. Now it will work.
Yes, sir. Yes.
Okay.
Sir, we can start from the next slide. So this slide was completed. We can start
Okay,
from next
okay.
slide. Yes, sir.
Okay. So we can develop there so many topologies using this brushless DC motor for using solar water pumping. So we can use the Hall position sensors. Basically, in BLDC motor, 3 Hall position sensors are there through which we can control the speed of DC motor. And we can develop another topology without using this Hall effect sensor, Hall position sensor. We will see that. So when we eliminate this Hall position sensor, that topology will be called position sensorless based BLDC motor drive. And then we can categorize the configuration of solar water pumping system like standalone PV generation system and grid connected PV generation system. Standalone PV generation system means we will connect a brushless DC motor pump with the solar pumping solar system. There will be, and that system will be completely isolated. There will be no utility grid. Means our solar panel will provide power to the brushless DC motor pump only. That is sufficient. But in case of grid connected PV generation system, there will be a utility grid, and our solar system will be interfaced with the utility grid. So in case of more power requirement, we can draw some power from the utility grid, or in case of excess power generation, we can transfer the power generated from PV array into the utility grid. That will be the grid connected PV generation system. Now, in standalone PV generation system, we can develop a double stage PV generation system or single stage PV generation system. So this is double stage means the number of converters. When the number of converters is 2, then it is called double stage. When the number of converters is 1, then it is called single stage PV generation system. So it is actually the number of converters. Then in case of grid connected PV generation system, that can be classified based on the control. When the control is unidirectional power flow control, that is actually unidirectional power flow control based solar water pumping system. And when there is bidirectional power flow control means power can be transferred from solar panel to the grid, and power can be transferred from grid to the motor pump. So power can be transferred in both ways. That's why it is called bidirectional power flow control. And for double stage PV generation system, we can use any type of DC to DC converter, that is a DC-DC boost converter, or DC-DC buck converter, or DC-DC buck boost converter. So any DC to DC converter we can use for double stage PV generation system. So this topology, you can see this is actually a double stage solar PV fed BLDC motor drive for water pumping. And why it is called a double stage? Because you can see there are two converters here. First is this DC to DC boost converter, and second converter is this 3-phase voltage source inverter. The role of this first converter, that is DC-DC boost converter, is any problem?
Actually, someone has unmuted themselves. So from the organization side, we have muted them. Sorry,
Okay.
sir, for the disturbance.
Okay, so role of this first DC-DC boost converter is to obtain the maximum power point of the solar PV array, because what we want is we want to try to get maximum output from the solar PV array. So in order to get maximum output from solar PV array, we generally use some MPPT technique, that is called maximum power point tracking. MPPT means maximum power point tracking. So to implement that maximum power point tracking technique, we need some converter. So that's why this DC-DC boost converter is used to get maximum power point of solar PV array. So that is the role of this DC-DC boost converter. Now the role of this second converter, that is 3-phase voltage source inverter, is to control this brushless DC motor. Now you can see here the input of this 3-phase voltage source inverter is DC. This VDC is the input of this 3-phase voltage source inverter. Now the output of this 3-phase voltage source inverter is that will be a 3-phase AC voltage through these 3 phases, and that 3-phase AC voltages will be fed to the stator windings of this BLDC motor. 3 currents are flowing. You can see ISA, ISB, ISC. So these are the stator currents, and this there is a water pump. That water pump is coupled through this BLDC motor. These are the 3 Hall signals, H1 to H3. So these are the 3 Hall position sensors actually. This Hall position sensor gives 3 Hall signals, and that 3 Hall signals are used for the speed control of BLDC motor control. We may also need the sensing of 3 phase currents, okay, phase A, phase B, and phase C, to control the current of this brushless DC motor, to control the stator current. Now from this side, we are also sensing the DC bus voltage, and that DC bus voltage is controlled to control the speed of the BLDC motor. So how many sensors we need? We need this voltage sensor here at the DC bus of voltage source inverter. We need 3 current sensors here, 3 stator current sensors. We also need these 3 Hall position sensors, and using this signals, we are generating the 6 switching pulses here, S1 to S6. 6 switching pulses are generated, which are used to operate the 6. So these 6 pulses are generated side using is increased. So there are like Quaterman observe, we have incremental conductivity. There are so many artificial intelligence based MPPT techniques. So
Hello, sir. Hello. Hello. Hello.
am I audible?
Sir, disconnected, sir, in between, and the voice is breaking in between.
Now I am audible?
No, sir, it's not clear, sir.
Not clear.
Oh, now it's clear, sir.
Okay, okay. Okay, I will repeat. Okay, so here in this topology, how many signals we are sensing is, we are sensing this DC bus voltage of voltage source inverter. We are also sensing 3 stator currents, ISA, ISB, ISC. Okay. We are also sensing these 3 Hall signals, H1 to H3.
Sir, the screen is not shared, sir. The PPT is not showing.
Okay. Screen is visible?
Yes, sir. Screen is visible, sir.
Okay, okay. Right. So now you get this is one voltage to send the receiver voltage, 3 sensors to send the state.
Hello. Hello, sir. Hello.
Hello.
Sir, yes, screen is not shared, sir.
Okay.
Now reduce.
It is visible now.
Yes, sir.
Okay. Okay, so this is very simple topology, double stage topology. So here we are using this DC-DC boost converter, a 3-phase voltage source inverter, a brushless DC motor, and a water pump. So our main objective is how we can reduce the cost of this topology, how we can actually reduce the complexity of this topology, so that the middle class farmers of India can afford the solar water pumping system. How we can make it affordable. So as I said, left hand side we are using INC MPPT, that is incremental conductance maximum power point tracking technique, and this technique is used to obtain the maximum power from the solar PV array. And especially this DC-DC boost converter is used for MPPT only. So this incremental conductance MPPT also needs the sensing of PV array voltage and PV array current. So one voltage sensor and one current sensor is required here. So how we can reduce this, means how we can make this topology simple. So this system, this is our proposed approach. So which stages we have eliminated here, which sensors we have reduced. So you can see this topology, this DC-DC converter is completely eliminated, right? This DC bus voltage sensor is also completely eliminated. And this H1 to H3, these are the Hall position sensors. These Hall position sensors are also eliminated. So when we eliminate this DC-DC boost converter, means one converter stage we will eliminate. Now that will be a single stage conversion. Only voltage source inverter will be there. 3-phase voltage source inverter will be there. So that will become a single stage solar water pumping system. So you can see this topology now. Sensorless BLDC motor drive for water pumping. You can see, because we have eliminated a DC-DC boost converter. Now this 3-phase voltage source inverter is directly connected across this solar PV array. Now this 3-phase voltage inverter will play double role. First it will control the speed of brushless DC motor, and second, it will also track the maximum power of solar PV array. So maximum power point tracking as well as the speed control of BLDC motor will be performed through these voltage source inverter only. So this will play a double role. So now we have eliminated this DC-DC boost converter. So obviously we have reduced the cost of the system. And then it is called a sensorless BLDC motor. Why it is called sensorless? Because this Hall position sensors H1 to H3, this has been completely eliminated. Why we have eliminated this Hall position sensor? Because the reliability of this Hall position sensor is not good. The probability of failure of this Hall sensor is very high. That's why the system is not reliable. The performance of the Hall sensors are actually temperature dependent, right? And other drawbacks are like it needs very precise mounting on the stator. If the mounting is not accurate, then the performance of motor will not be good. So these are the drawbacks of this Hall sensor, Hall position sensor. That's why we actually eliminate this Hall position sensor, and we have made this topology a sensorless BLDC motor drive. Okay, because we want to make our system maintenance free. In case of submersible pumping, submersible water pumping, where our motor along with the pump will be inside the ground, inside the earth, then we cannot take our motor pump set, we cannot take out every time for the maintenance. Okay, so what we can do, we can make our system reliable so that it can be maintenance free. So with this Hall position sensors, we cannot make our system reliable. We cannot make our system maintenance free. That's why we have eliminated this Hall position sensor, and we are controlling our motor without this Hall position sensor. That is called position sensorless BLDC motor drive for water pumping. So here also MPPT, we are not compromising with the MPPT. MPPT is enabled in this system also. So instead of sensing the Hall positions, rotor positions. What we are doing here, we are using the line voltage sensing. Here we are sensing the 3 line voltages, VAB, VBC, VCA. And using these 3 line voltages, we can generate the virtual Hall signals, because Hall signals are compulsory for the electronic commutation of this BLDC motor. So here we have eliminated this Hall position sensors. So how we will generate the Hall signal?
Hello, sir.
Yes.
Sir, what is the solar PV rating?
PV rating. Yes, I will.
Yes,
I
sir.
will come to that also.
Okay,
Okay, I
sir.
will come to that.
Okay. Yes, sir.
I will come to that.
Yes, yes. The students, participants are asked to.
Yes, I will come to that. I will show the completely the experimental results. What are the specifications of BLDC motor, the specifications of solar PV array, everything I will show,
Yes,
so
sir.
that we can get clear understanding.
Yes, sir.
So here, what I was saying that I have used these line voltages, and using these line voltages, I have generated the virtual Hall signals. And through these virtual Hall signals, we have generated 6 switching pulses. And the incremental conductance MPPT and motor control, these 2 control techniques are actually combined here in the single stage topology. We have combined these 2 control systems, incremental conductance MPPT and motor control. These are combined through these logic gates and logic gates. And ultimately, we are getting the 6 switching pulses to operate this voltage source inverter. So through this scheme, we can get maximum power point tracking also. We can control the motor also without any DC-DC converter. So that is the advantage of this system. So you can see this in this system. This is called a single stage, which is also called DC-DC converterless PV system for water pump. It has position sensorless control, means we are not using any Hall position sensors. This has reduced the DC bus capacitor. You can see this is the DC bus capacitor, and the value of this DC bus capacitor is very less. We can see how we can calculate this value through these mathematical expressions. There is no closed loop for speed control. Here you can see there is no closed loop for speed control. The speed of BLDC motor will be adjusted through the power generated by the PV array. If the power generated by the PV array is reduced due to this weather condition, then the speed of BLDC motor will be automatically reduced. If the power generated by the PV array is increased, then the speed of BLDC motor will be automatically increased. So the speed is automatically adjusted through the power generated by the PV array, through the open loop control simply. So there is no closed loop control here. So salient features are, it has high efficiency because we have used a very high efficiency BLDC motor. That's why overall efficiency of the system is improved. Along with that, we have eliminated the DC-DC converter. So actually losses in the DC-DC converter will be around 5 to 6%. So when we eliminate the DC-DC converter, we can also increase the overall efficiency. Then the system is economical. Why it is economical? We know the cost of BLDC motor is high. So why we are saying that the system is economical? Because we are employing a very costly BLDC motor. But still we are saying that system may be economical. Why? Because for the same power output, we can reduce the size of panel, because we are using high efficiency motor. So we can reduce the size of panel for the same amount of water delivery when we compare with the other motors. Then the system is compact. It is compact because we have eliminated one conversion stage. We have also reduced the size of our motor drive system. And it is reliable for submersible water pumping. It is reliable because we have eliminated the Hall position sensors. And in place of that Hall position sensor, we are using the reliable Hall effect voltage sensors. So that will become a reliable, especially for submersible water pumping system. Now you can see the specifications of BLDC motors. So for the experimental validation, I have used a 1.3 kilowatt BLDC motor here. Then speed of BLDC motor is 3000 RPM. DC bus voltage rating is 270 volt. It has 4 poles. Moment of inertia is given. Stator current rating is 4.3. Voltage constant, torque constant, face-to-face resistance, face-to-face inductance. Everything is given. So these are the specifications of BLDC motor which is used for the experimental validation. Now, when we use 1.3 kilowatt BLDC motor, then now the question is how much power, how much PV panel is actually required for this 1.3 kilowatt BLDC motor. So accordingly, I have designed a solar PV array. Right? We know that we need 1.3 kilowatt BLDC motor. So for 1.3 kilowatt BLDC motor, how much input power is required? If the output is 1.3 kilowatt, then input must be greater than 1.3 kilowatt, because there will be some losses in the BLDC motor. There will be some losses in the voltage source inverter, right? So assuming that losses, we can select the solar PV array which has power rating somewhat more than 1.3 kilowatt. Okay, so here we have chosen PV panel of 1450 watt. So this 1450 watt will be sufficient to operate the BLDC motor at its rated speed and rated torque. So this 1450 watt is somewhat higher than 1.3 kilowatt, obviously, because we are assuming some losses in the voltage source inverter, we are assuming some losses in the BLDC motor. Now, accordingly, we can calculate how many numbers of series panels and how many numbers of parallel modules are required. You can see this HB 1290. So this is a module, PV module, which has number of cells 36. It has maximum power of 90 watt. It has open circuit voltage 21 volt and short circuit current 6.4 ampere. Right. So this is for one module. So we will take this module to design our solar PV array according to our requirement. So what is our requirement? Our requirement is 1450 watt solar array. Now we can calculate the voltage of this solar PV array, and we can calculate the current of solar PV. How we can calculate the current is IFPP, that will be equal to power divided by voltage. So power is 1450 and voltage is 270. This 270 is this voltage. This is the DC bus voltage of our BLDC motor, and you can see here this BLDC motor, this is directly connected across the PV array. So this voltage is 270 volt, which is the input voltage of DC motor, and the same voltage is nothing but the voltage of PV array also, because this is directly connected. So we can take 270 volt as the voltage of PV array. So here 1450 watt power divided by voltage, that is 270 volt. So that will give 5.4 ampere. So that should be the current of our PV array. Okay, voltage should be 270. Current should
Sir, I have a doubt, sir, here.
Yes.
Sorry to interrupt. Sir, in the case of double stage, when we are using boost converter,
Okay.
so its purpose is to track the VMP, so
Right.
that we get maximum. So then what about the DC link voltage, sir? I mean, my doubt is whether it will do only MPPT function or boosting also, or both.
So main objective is to get the MPPT. Main objective is not to boost the voltage, right? So the voltage rating, that is 270 volt, that is the voltage of our BLDC motor. So we cannot change that voltage. That is the maximum voltage of 270. That is actually the rated voltage of BLDC motor. So that if we use this DC boost converter here, so here at this point, the input of this three-phase voltage source inverter will be 270 volt. That will be fixed. Now, if I want to boost, if I want to use the boosting feature of this boost converter, then I will choose panel which has a voltage lower than 270 volt. Okay, then only it will boost. Means voltage of PV array should be less than 270 volt. Let's say it is 150 volt. So then voltage will be boosted from 150 volt to 270 volt using this boost DC boost converter. Otherwise, we can simply, if we don't want to use the boosting feature of this boost converter, then I can use, I can select a PV array which has the voltage of 270 volt. So input voltage is also 270 volt. Output voltage is also 270 volt. Because our main objective is to obtain the maximum power point tracking. Our main objective is not to boost the voltage. Why I will boost my voltage? I can increase the voltage of PV panel. So then I don't need boosting. If somehow we don't have a sufficient number of modules to connect in series, means somehow we are unable to increase the voltage rating of our PV array, then I must use the boosting feature of this boost converter. Okay, but if I have a sufficient number of series modules and I can provide sufficient voltage, then I don't need to use boosting feature.
Sir, in that case, if the number of PV panels are less, along with the boosting, can we able to obtain MPPT also?
Yes. Because boosting feature is the actually basic feature of boost converter. It will obviously boost.
But when we are selecting VPB as equal to VDC, then it is not doing MPPT, sir. That boosting, no? So there
Yes,
I am
it
getting.
will not do boosting, but it will provide MPPT function.
So it
Right.
depends on what, sir, like what we have to change in that control.
Okay, let's say I have chosen 270 volt PV array voltage and output voltage is also 270, that I have selected. But you can assume the weather condition in the morning, that will not be 270 volt. Right? In the morning it will be less than 270 volt. Then it will use boost feature also. Because weather condition is continuously being changed. No?
Yes, sir. In both the cases, in two cases, because we cannot predict when that situation may come.
Right.
So how it will be taken place practically, like in the circuit, what are the changes will take place? Whether we have to do anything, add additionally, or it will be done automatically.
It will be automatically, because what will happen, we are through the MPPT, what we are doing, you can see this diagram. Through the MPPT, we are just adjusting the duty cycle. The output of MPPT is duty cycle, right? So by tracking the maximum power, it will generate duty cycle. So when the weather condition is changed, duty cycle will be automatically changed. And when the duty cycle is automatically changed, then that boost converter give different output voltage based on the duty cycle.
Excuse me, sir.
Sir, actually here, when I go through the algorithms, MPPT algorithms, as we are writing the algorithm with respect to changing the MPPT voltage, or not with respect to the output voltage of boost converter.
Yes.
So actually there I am getting a little bit confused, sir.
Yes, so when you change duty cycle, we are controlling through the MPPT, actually we are controlling the input voltage of boost converter, right? Or the voltage of PV array. But as per the basic function of boost converter, the output voltage will also be changed as per the duty cycle. Although we are controlling the input voltage only, but when we control the input voltage and duty cycle is also continuously changed because of the weather condition. So output voltage will also be changed. So that 270 volt which I have shown here in this table, which is the rating of this inverter. Okay, that 270 volt is actually at 1000 watt per meter square at standard test condition. But when the radiation gets down, means when the radiation is, let's say 500 watt per meter square, let's say during morning or during evening time, then that 270 volt will also be reduced automatically. In that case, what happens? The duty cycle of this MPPT will also be changed, and input voltage of this PV array will also be changed. So everything will get changed. The input voltage, output voltage, and duty cycle, all these parameters will be changed based on the weather condition. And at the same time, the boost converter will perform its basic function, means it will be able to boost the voltage, and it will also be able to obtain the maximum power point. Maximum power point, how we will get? Because the voltage, PV array voltage is being adjusted. So we will get maximum power point.
Excuse me, sir.
Sir, suppose if DC converter is not there, as you the case what you mentioned, during the low irradiance condition, anyhow, irrespective of PV, we have to maintain the DC link voltage constant for effective power flow. So in that case, how that voltage will be taken care of during the low irradiance condition?
Yes, during low irradiance condition, that 270 volt reduced, okay, voltage will be reduced, then because of the speed of the BLDC motor will also gets down, it will be reduced, right? And then what happens, motor will get less power, so water delivery will be reduced, amount of water delivery will be reduced.
I mean, in that case, can we able to maintain DC-link voltage even during at low irradiance, sir? Is there any
Means
method?
if you want to maintain a 270 volt fix.
Yes, sir. Yes, sir.
So in case of this two-stage topology, we will be able to maintain the voltage as 270 volt. But in case of single stage, we cannot maintain voltage as 270 volt because the DC link voltage is same as the P-vary voltage. So if we maintain at same 270, we will be unable to get the maximum power point. Because to get the maximum power tracking, that voltage must be variable.
Sir, will this single stage topology works for the panel array if the rating is less, like it will not give 270 volts, like maybe like 200, will it work the single stage conversion?
Yes, that will work. Only thing is that BLDC motor will get less power, so it will deliver less amount of water.
Okay.
So,
what
sir,
if-
suppose
yeah, if PV panel has got a lot of local maximas, then how the MPPT responds?
In case of partial setting, then you have to. There are so many techniques, so many MPPT techniques to deal with this partial setting condition. Also, then we can use some technique which can address the partial setting condition. Then we can get maximum power also. Simple. I am using here incremental conductance MPPT. This is simple MPPT algorithm which may not address the partial setting condition. But if we assume that condition that there may be partial setting, then you can modify this MPPT technique only. So that for the many number of local maxima or minima, that MPPT can be achieved.
Okay, sir.
In both single stage and double stage, we can do that, assuming the partial setting condition.
Sir, good morning, sir.
Yes.
Sir, my doubt is that nowadays the BLDC coming with the voltage rating of 48 volts, sir, of same
Yes.
power rating.
Yes.
And the panels are also coming with the rating of 36 to 40 volts, sir. That is a open circuit voltage. So
Yes.
how could this same thing can be designed for this specific voltage rating of the panels and the BLDC motors? This your proposed diagram, the topology.
So when we have 48 volt BLDC motor, then we have to select our PV array such that we can meet the requirement of 48 volt. In case of single stage, in case of double stage, we are free to select any voltage of PV array because we have this boost converter in between the PV array and BLDC motor, right? So we have 48 volt BLDC motor here at the output of boost converter, and at the input we can use the voltage rating less than 48 volt because we have boost converter. But in case of single stage, what we can do is we can select our solar panel which has the voltage around 48 volt, which has the voltage not more than 48 volt, right? So this 270 volt I have taken just for experiment. Otherwise, we can take any motor like 48 volt motor also.
Yes, sir. I have done the experiment on that only, sir. I have taken a rating of 40 volts open circuit voltage of PV panels and drive a motor of 750 watts, sir, of voltage rating 48 volts. 48, yes, sir.
So
Second,
how you are operating at rated speed because you are providing less voltage from the PV array.
power is getting more necessary. I am inputting a BLDC motor rating and having of 21 amperes, sir,
Okay.
rated current. So I am making the 4 panels in parallel, sir, so that it can supply a voltage of more than 27 ampere and voltage of around 36 to 40 volt. I am getting boosted. Then I am applying a boost, sir, DC-DC power conversion stage in between
So
them.
you are using boost converter, na?
Yes, sir. Yes, sir.
Yes, sir. You can boost up to 48 volt.
Yes, sir. Yes, sir. Because my voltage stage is less, sir, on the components. So sir, can I know the equations relating the back EMF and stator EMF? I'm not getting, sir, in the
Back EMF and
stator current EMF relating to the power rating, what I am choosing it further also.
Okay, I will show some equation.
Okay, sir. Thank you, sir.
Sir, one more query, sir, here in the single stage.
Okay.
Sir, suppose if we include the grid, if the grid is connected to this single stage, in that case, how we will maintain the voltage relations? Because the inverter output voltage
Are you
should
able
match
to
with
see
the,
this diagram?
yes, sir.
Configuration of grid interactive solar PV powered BLDC motor driven water pumping.
Yes, sir. Yes, sir.
Okay, so can you understand through this diagram what you are asking?
Here the grid is connected at the input of inverter.
You can
sir,
see
but
this is single
I'm-
phase. This is single
Yes,
phase
sir.
grid here.
Yes, sir. But I thought connection of grid at the input of BLDC motor after the output of three-phase VS, sir.
After the output of three-phase
Yes, sir.
inverter.
Yes, sir. Yes, sir. Here where ISA, ISB, ISA are indicated.
So at this point, you are asking, can we connect grid here?
Yes, sir.
No, we cannot connect grid here because BLDC motor needs trapezoidal voltage input. It doesn't need sinusoidal input voltage, but it has sinusoidal input voltage. So we cannot connect this grid at this point because BLDC motor must have trapezoidal input voltage only. It doesn't have sinusoidal.
So it means we cannot use BLDC motor without VSI. Is it like that, sir?
Yes, yes.
Because-
VSI is compulsory. Compulsory. It is compulsory.
Okay, sir. Thank you.
And grid has sinusoidal, so we cannot connect at this point the BLDC motor. Because voltage are different, na? It has trapezoidal and grid has sinusoidal. So we cannot match the frequency, we cannot match the voltage waveform. For the synchronization, we must match the frequency and voltage. That is the necessary condition. Grid frequency is 50 Hertz, but the BLDC motor frequency may not be 50 Hertz. Just like in the system, the motor which I have selected has the frequency 100 Hertz. Fundamental frequency of BLDC motor is 100 Hertz, which I have chosen here. So we cannot
Okay,
connect
sir.
to the grid. Okay,
Okay,
so
sir. Thank you.
here,
Namaskar, sir. Hello.
yes, yes.
Sir, any disadvantage of using single stage as compared to double stage in a standalone PV system? Any
Yes.
disadvantage?
Only disadvantage I can say is we are just losing the flexibility in the control because when we use this double stage topology, MPPT control is separate. Okay, MPPT control is separate. It doesn't. It is not related with the motor control. These are independent controls. No? MPPT is different, independent. This motor side control is also independent. Now in single stage, what happens? We are combining MPPT control as well as motor control. So if there is any problem in MPPT side or if there is any problem in motor side, that problem, it will be very difficult to identify that which side is creating problem, right? And also when we combine two control systems, that creates actually loading on the processor because two controls are combined. So that is actually a small drawback of the system, but I have validated the system and the system is properly running. That system can be actually employed in the real field. There is no problem. It will work properly.
Hello, sir.
It was a large fluctuation in D will be there not to obtain MPPT while we are switching the switches of the three-phase VSI. Initially to obtain the MPPT point. So it will not affect the system?
Initially.
Initially to obtain the...
That will be for very small period, let's say for 1 second or 2 seconds. Just it is actually a starting process only. Just for the starting of BLDC motor, once the motor attains some speed like 500 RPM, then that will work properly.
Okay. Sir, for single stage, we have to choose the PV panel rating just equivalent to the BLDC voltage rating. Voltage, I am talking about voltage.
Yes,
Near to
yes.
that. Very much near to that.
Yes.
Okay, sir.
So we have to just take care of the voltage rating of the BLDC motor, voltage rating and current rating. Because if it is 48 volt BLDC motor, so we cannot provide an input of 100 volt.
Yes.
Because the voltage is variable. When the temperature is increased or decreased, the voltage may get more than 48 volt.
Yes, sir.
So we have to take care of the over voltage protection or over current protection of the BLDC motor.
So sir, like for a 2 ampere BLDC motor rating, like you are using 270 volt around, so starting current will be higher.
Yes.
And in 48 volt or 20 ampere rating BLDC motor, there also starting current will be much higher. So we have to use over current rating protection for the motor.
Yes, we have to always that must be enabled in any system. Then only we can say that our system is reliable.
We can't use. So you have used any controlling techniques to
Control the starting
cut
current,
down the starting current.
Yes. I will show the result. I have used some techniques which can reduce the current during starting.
Okay.
Otherwise, what happens? Starting current is very high. So during starting only stator winding will be damaged. So that protection must be enabled to prevent the overcurrent.
Like sir, we are using the same. Actually, we are obtaining the voltage immediately. We will obtain the voltage in 1 or 2 seconds. We will get the voltage. So motor rating voltage is being obtained in a very few duration. So the starting current will be much higher. Like in your paper, you have used buck boost converter also, where firstly we are getting buck and then slowly we are proceeding towards boost. So at that moment of time, the voltage is rising at some pace, little bit slower pace. So this is how the starting current can be reduced.
So we actually through the MPPT we are adjusting the duty cycle, right? So
Yes.
if I start with 0 duty cycle, then current will also increase slowly. It will not increase abruptly, because I will start with 0 duty cycle in MPPT itself.
Okay.
And then I will increase the duty cycle slowly.
So slowly, for that we have to use filter. Any filter?
No. I will filter is not required. I will keep this step size or perturbation size less. Okay, and then its duty cycle will be updated at very slow rate. It will increase very slowly.
Okay.
Because
like sir,
MPPT can be faster, okay, but the motor is not faster. Motor has some inertia. It will take some time to get its speed. Na? So we have to actually match the time constant of our MPPT system and inertia of our motor.
Okay.
So in case of motor system, we cannot track the maximum power at very fast rate. We have to slow down the tracking actually.
Okay, so but the disadvantage for this is that for that particular duration of time, we are not utilizing the power. Every time when we switch on, for that duration of time, slow
For
tracking.
how much duration? That is for 1 second. This is
that
will be for less than 1 second only.
Okay.
Okay, how much the inertia of motor for to attain the inertia of BLDC motor is actually very less. Actually, to attain the rated speed, it will take only 2 seconds or 3 seconds maximum.
Okay.
Induction motor inertia is very high. It takes actually 1 minute also. But inertia of BLDC motor is less. It will not take more than 2-3 seconds.
Okay, sir.
Hello.
Thank you,
Sir, I have 2 general doubts, sir. So generally in most of the literature, I can found that along with PV array, we are using VSI, voltage source inverter. So why can't we go for CSI, sir? And that is one. And second thing is, most of the cases I can see only incremental conductance MPPT. Is there any specific reason of using only this one? Can you please elaborate this?
Yes.
MPPT, sir.
Okay. So
CSI and
okay. I got your question. So basically, this perturb and observe MPPT and incremental conductance MPPT. So these are the basic MPPT techniques. These 2 are basic MPPT techniques, and these are actually practically used nowadays. And accuracy wise, both these MPPTs are same. Both give same accuracies. In publication, people may be confused. Somebody says that incremental conductance is better. Somebody is saying that a perturbed observer is better. But both these techniques are exactly same in terms of accuracy. And we talk about other MPPT techniques which are being developed nowadays. So just to publish number of papers, number of articles, people are doing anything. But when we use any system in practical products, then we have to think about the cost of the system, reliability of the system, right? And performance of the system. So before applying any technique into the actual product, we always think about these parameters. We cannot randomly apply any MPPT technique in practical system. Okay, so first is perturbed observe, second is incremental conductance. These two MPPT algorithms are exactly same. Accuracy wise, if you go for publication, somebody may confuse you that MPPT incremental conductance is better than perturbed observe. Okay, or perturbed observer is better than incremental conductance, but that is not true. Both MPPT systems are exactly same and are being used in practical system. The MPPT, this incremental conductance needs current sensing and voltage sensing. Two sensors are required, current sensor and voltage sensor. Similarly, in perturbed observe, we need two sensors, current sensor and voltage sensor. So cost of sensing is same in both MPPT techniques. Other is next will be the DSP system, digital signal processor, because that MPPT coding, that logic will be written in the DSP system. So cost wise, these two MPPTs are same. Okay, then if you use another MPPT techniques like fuzzy logic systems are there, these artificial systems are there. There are so many other MPPT techniques are there. So you will get same result. There will be no specific advantages of other MPPT techniques than the incremental conductance in perturbed observation. But for the publication, you can write any number of MPPT techniques. That doesn't matter. But for practical use, you have to think which MPPT techniques we have to use, right? And second is the current source inverter. We can use current source inverter also. You can find many application, many publication of related with BLDC motor with current source inverter also. Only difference is what? When we use current source inverter, then in place of this capacitor, we have to use a bulky inductor. So we can use a bulky inductor, size of inductor will be very large, cost of inductor will also be very large. Okay. And performance wise, both will give same result. You can use current source inverter also. Only problem is that we must use a bulky inductor, which will be very high, means that will be costly, as well as size of that inductor will be high. That is the reason only.
Hello, sir.
Yes.
Sir, in single stage topology, can we use the battery bank as a backup to maintain the DC link voltage in low irradiation condition, like it can support the DC link voltage?
In single stage.
Yes, sir.
So
Means,
at which point you will connect this battery at the output of PV panel?
No, means in shunt connected, sir, across the DC link capacitor.
So yes, means across at the output of PV panel only, no? That is the DC link.
Yes, sir. Yes. Yes, sir.
So
yes, sir.
Without any converter, can you connect a battery? Without any converter, you cannot connect a battery because the battery voltage will be constant.
Yes, sir. We
So
need
when the
like
battery
bidirectional topology.
So when the battery voltage is constant, what we want actually in single stage topology, the DC link voltage should be variable. It should not be constant. If it is constant, then we cannot maintain the MPPT, because to maintain the MPPT, that voltage should be variable. That voltage should be varying according to the atmospheric condition. Okay. During morning, value of voltage will be different. During evening, value of voltage will be different. It will be continuously varying actually, and it will be equal to the voltage at maximum power point. PV voltage at maximum power point. But when you connect a battery, that voltage will be fixed. Let's say at 48 volt. So when the voltage is fixed at 40 volt, and that is not variable, so obviously we we will not be able to obtain MPPT. So voltage must be variable actually in single stage system.
Okay.
Hello, sir.
And sir, can we get the means? Can you explain the design calculation? That how can we form this closed loop system?
Can we skip?
No, sir. Means I want to say that can you explain the design calculation? Means how
Yes,
you
yes,
have done this?
Okay, I am coming to that. So this is the table showing the specifications of BLDC motor. Okay, 1.3 kilowatt BLDC motor, 3000 RPM. And accordingly, we are designing this solar PV array. As I said, we have selected 1450 watt solar PV array, and accordingly, since we have the value of voltage which is 270 volts, so these values, this 1450 watt, this 270 volt, all these values are taken at standard test condition. Standard test condition means 1000 watt per meter square, 25 degree centigrade temperature. At this condition, we have taken 1450 watt peak power from the solar PV array and 270 volt, which is actually the voltage rating of BLDC motor. So power divided by voltage is the current 5.4 ampere. Now we have the voltage 270, we have the current 5.4, we have the power 1450. So number of modules connected in series are given by voltage at maximum power point VMPP divided by VM. So this VM is the voltage of single module, which is shown in this table below. Voltage of single module is given here 17 volt. Voltage of single module is 17 volt. So total voltage is 270 divided by 17 volt is 16. So we need 16 series modules. Similarly, number of modules connected in parallel. This is total current divided by current of single module. So total current is 5.37 from this equation, and current of single module from this table is 5.4. Last row. So 5.37 by 5.4, that is 1. Right. So to design the PV array of 1450 watt, we have to connect 16 modules in series. Okay, 16 modules in series and 1 in parallel. Then we will get 1450 watt at 1000 watt per meter square radiation. And that 1450 watt will be able to run the BLDC motor at full speed and full torque. Full speed it means 3000 RPM. So accordingly, we have designed the solar PV array. Then we can calculate this DC bus capacitor, which is connected at this point. We can calculate this DC bus capacitor. This voltage source inverter will be generally operated at high switching frequency. Okay. So we know when the switching frequency is increased, value of capacitor is decreased because capacitor is inversely proportional to the switching frequency. And very simple equation here for the calculation of capacitor. This is very simple equation. Just IC is equal to C dV by dt. Capacitor current is equal to C dV by dt. That is the simple expression. Using that simple expression, we can calculate the capacitor. Okay. And current value, what we will put? We will put the current is equal to the short circuit current, because maximum current which can flow through this capacitor is short circuit current only. Okay. Current cannot be more than short circuit current of PV array in any case. So maximum current is 6.4 ampere. That is the short circuit current of PV array. Right here, the 6.4 ampere is the short circuit current of PV array. So we have taken this maximum current 6.4 ampere. Okay, IPV is equal to 6.4 ampere, which is the short circuit current of PV array. Is the current supplied by the PV array, right? And you can apply here. You can see this is the node. You can apply KCL, Kirchhoff current law here. So this IPV is incoming current. Okay, and that IPV will be divided into two parts. First part will flow through this capacitor. Second part will flow through this DC bus. Okay, and actually ripple component of IPV will flow through this capacitor, and pure component will flow through this DC bus. So we have applied a KCL here. So this will be the KCL equation. IC, that is current flowing through the capacitor, will be equal to IPV minus IDC. IPV is taken as 6.4 ampere, that is short circuit current. Okay. Worst case is that, worst case what we have assumed that all the current.
Hello?
Yes.
Sorry to disturb you, sir. Just after completion of this topic, we will like to take a short 10 minutes of break.
10 minutes?
10 minutes of break.
Okay, so we can take break.
Okay, so we will resume at 11:55, sir.
Okay, okay.
Okay, sir. Thank you. Hello, sir. Can we restart the session? Sir, can we start?
Okay, candidates have joined now.
Yes, sir. Yes.
Okay. PPT is visible.
Yes, sir.
Yes, sir. Yes.
Any other question? Then we will move forward. Okay. So through this basic equation, we have calculated the value of capacitor here. So I have taken the switching frequency 5 kilohertz, 6.4 ampere is the short circuit current, and 336 volt is actually the open circuit voltage. And this 0.02 is actually the 20% ripple which we are allowing through the voltage. This is the ripple on the voltage across the capacitor. 20% voltage ripple we are allowing across the capacitor. So capacitor value is just 200 microfarad. So in case of single stage system, capacitor value is just 200 microfarad. Otherwise, in case of this two stage PV system, the value of capacitor is large, around 2000 microfarad. So we can reduce the capacitor size in single stage PV system. Now this slide shows the various control system involved with this solar water pumping. So how many control systems are there? First is the incremental conductance MPPT of solar PV array, which is shown in this flow chart in this yellow box. This shows the incremental conductance MPPT algorithm. Then the second is electronic commutation of BLDC motor. So this table, which is shown in this green box, this shows the electronic commutation of BLDC motor. Then third, switching pulse generation of VSI. So this blue box, this shows switching pulse generation. So how the switching pulse is generated, we are combining the incremental conductance MPPT and electronic commutation, and through this combination we are generating the PWM pulses for the VSI. We are using this end logic to combine these two control techniques. Then sensorless speed control of BLDC motor. So sensorless means, as I said, that we have eliminated the Hall position sensors. So anyhow we have to generate the virtual Hall signals. How we are generating the virtual Hall signals? Using this 3-line voltage. Instead of sensing these 3-line voltages, we can sense 2-line voltages also, and 3rd-line voltage can be generated using VAB plus VABC plus VCA is equal to 0 equation. And so these line voltages are actually converted into 3 back EMFs. Through the mathematical expressions, we are converting this line voltages into back EMFs, and using the zero crossing of this back EMFs, we are able to generate the virtual Hall signal. So these are the various steps. So first we will go through the electronic commutation of BLDC motor. What is electronic commutation? In conventional DC motor, that is mechanical commutation. Here it is electronic commutation. It is called electronic commutation. Why? Because we are commutating the current through the inverter. That's why it is called electronic commutation. So how this electronic commutation is performed? You can see this table. Following the rotor position, the Hall sensors provide 3 Hall effect signals on 60-degree span. So this first column shows the rotor position, 0 to 60 degrees, 60 to 120 degree, like that. And according to this rotor position, the Hall signals will be H1, H2, and H3. So there will be a particular sequence of Hall signals. Like for 0 to 60 degree, sequence will be 1, 0, 1. So H3 will be high, H2 will be low, H1 will be high, right? And then these 3 Hall signals are logically converted into 6 switching pulses, which is used to operate the VSI. Now, according to this sequence of Hall signals, we are operating the switches of voltage source inverter. Okay, so for 0 to 60 degree, Hall signal sequence will be 101, and accordingly, the switch S1 will be turned on and S4 will be turned on. Other switches will be turned off. So at a time, only 2 switches will be turned on. One will be top switch and another will be the bottom switch of another leg. So at a time, 2 switches will be turned on, but these switches will be from different legs. We cannot turn on the 2 switches of the same leg. Otherwise, there will be short circuit. So you can see this S1 is the top switch. S4 is the bottom switch of other leg. You can see this. This S1 is the top switch of first leg. S4 is the bottom switch of second leg. Okay, when the rotor position is changed, sequence of Hall signals will be changed, and the operation of the switches will also be changed. So this table must be followed for the proper commutation. And through this commutation, current will be shifted from one phase to another phase. That is called a commutation. When this table is properly followed, then motor will get proper acceleration and it will produce required torque and speed. Now, this is the functional sequence of sensorless technique. So basically, first we are converting this line voltages VAB, VBC, and VCA into back EMFs EAN, EBN, and ECN through this sequence. So EAN is equal to VAB minus VCA divided by 2. So through this equation, we have converted these line voltages into phase voltages. What is our target? Our target is to identify the zero crossing of these back EMFs. So why we are using these line voltages? Because we cannot directly access the back EMF signals. Back EMF signals are internal signals. Okay, these are internal signals we cannot directly access. So what we can access? We can access the line voltages. That's why we have set the line voltages here. We have converted this into phase voltages. Now our objective is to find out the zero crossing of these back EMFs. Okay, and our ultimate objective is to generate the virtual Hall signals. In the first stage, that is line voltage to back EMF conversion. Okay, EAN, EBN, and ECN. Now we are using low pass filters in the second stage. Why we are using low pass filter is we can understand through this diagrams, through these waveforms. These are the waveforms of line voltages. Okay, waveforms of actually the phase back EMFs converted through the line voltages. So first is EAN, then EBN, ECN. These are the back EMFs converted through the line voltages. But you can see there are spikes. These are the spikes. Okay, and these spikes are confusing. These are creating unwanted zero crossing. Okay, you can see this is due to this spike. It is looking like this is the zero crossing, but this is not the actual zero crossing. Actual zero crossing is here. So these waveforms of this estimated back EMFs contain spikes due to freewheeling diode conductance. We know there are anti-parallel diodes connected across the IGBTs. Okay, and because of the conduction of this freewheeling diode, these are the unwanted spikes. So we want to eliminate this unwanted spikes, otherwise we will get wrong detection of zero crossing. We will not get exact zero crossing. So we want to eliminate these unwanted spikes. So to eliminate these unwanted spikes, we have used this low pass filter. This is the transfer function of low pass filter, omega c divided by s plus omega c. We can calculate these frequencies, crossover frequencies, omega c. Okay, and then this EAF, EBF, ECF. These are the filtered back EMF signals. Filtered back EMF signals. Now problem with these filtered back EMF signals are, again, this is the transfer function of low pass filter. Okay, low pass filter. So cutoff frequency we have determined on 2500 radian per second. This is omega c, 2500 radian per second. This is actually calculated as per the rated speed of BLDC motor, which is 3000 RPM. So considering both the phase shift and unwanted zero crossing, what happens when you decrease this cutoff frequency from 2500 radian per second, it will increase the phase delay. Okay, it will increase the phase delay. And when you increase this cutoff frequency, let's say if you take 5000 radian per second, then that can allow some unwanted zero crossing. Means some unwanted zero crossing may not be filtered. So that cutoff frequency should be properly calculated, right? Considering both the phase shift and unwanted zero crossing. So this is actually calculated at rated speed at 3000 RPM. Now, when we use this low pass filter, what is the problem? Then we have to design a phase delay compensator, because this low pass filter will introduce some phase shift. Okay, introduce some phase delay. You can see how much phase delay is introduced by this low pass filter. You can see this is 9.8 degree. The first one is the stator current. You can see the first one is the stator current, right? And S1, this is S1 is the switching pulse. S1 is the switching pulse, and last one is the S1F, that is filtered switching pulse. So how much phase delay we are getting? We are getting 9.8 degree of phase delay by using low pass filter. So this high phase delay is not acceptable, because that will produce oscillation in the torque. Okay, that will produce noise. Motor will not perform properly. Motor will not give proper output. Means its efficiency will get down. So we cannot allow this 9.8% of phase delay, right? Because it will give wrong detection of zero crossing. So we have to reduce this phase delay. So what we will do? We will design a phase delay compensator. So how we have designed this phase delay compensator? This is the transfer function of phase delay compensator, which is shown here in this diagram. You see this. This is stage. This is phase delay compensator, and this is the transfer function Ks plus omega C1 divided by S plus omega C2. Now we have to calculate the value of this constant K. We have to calculate the values of this crossover frequencies omega C1, omega C2. So these are the equations here. This is the transfer function of phase delay compensator, right? And we have chosen a 4-pole BLDC motor. So being a 4-pole 3000 RPM motor, fundamental frequency of the BLDC motor at 3000 RPM is 100 Hertz. Okay, 100 Hertz, and 100 Hertz is equal to 628.32 radian per second. Okay, so it is indicated that a phase delay of 9.8 degree occurs. So in this diagram, 9.8 degree phase delay, it corresponds to 3000 RPM speed, right? 3000 RPM means 628.32 radian per second. So using this data, we can calculate the value of constant K. Constant K is 1 plus sin theta d divided by 1 minus sin theta d, where theta d is the phase delay, that is 9.8 degree. So value of K is calculated 1.41. Then we can calculate omega C1 and omega C2. Okay, through these formulas, omega C1 is 545, omega C2 is 146. Okay, so now we will connect this phase delay compensator at this point. So when we connect this phase delay compensator, we will get the compensated back EMFs EAP, EBP, ECP. So these are the compensated back EMFs. So we can now see how much we have reduced the phase delay. So from 9.8 degree, you can see now we have reduced up to 2.7 degree. Okay, now phase delay is just 2.7 degree. So this 2.7 degree is somewhat acceptable. Okay, we cannot reduce this phase delay to 0 practically. That is ideal condition. Okay, so we have just reduced this phase delay up to 2.7 degree only, and that is acceptable actually. Then the next stage is to generate the commutation signals. Okay, so generation of commutation signals. How we are generating? We are comparing these back EMFs EAP, EBP, and CP. So that will give the virtual Hall signals. These are the ZA, ZB, ZC. So these are the virtual Hall signals. So using these virtual Hall signals, we can generate the 6 switching pulses according to that commutation table. Okay, so using this getting signals, we can generate S1, S2, S3, S4, S5, and S6, right? So this everything can be done inside the processor. We don't need external hardware component. Okay, all this logic from here to here, from here to here, from line voltage to back EMF up to the switching pulse generation, this everything can be done inside the digital signal processor. Okay, we can feed the transfer function inside the processor. We don't need to use any external hardware component, so that we can reduce the cost of hardware. Now we have generated the gating signal. Okay, now this shows some experimental results and some simulation results. I have simulated this system in MATLAB. So this is the MATLAB model. Then these are the results. I will come to the experimental result that will give clear understanding here. So this is the hardware setup. You can see here, these wires are coming from the solar simulator. So wires from solar PV simulator. So instead of using actual solar panel, I have used a programmable DC power supply, which has the feature of characterizing the solar PV curve and IV curve. So this gives the similar characteristics. So these wires are coming from solar PV simulator. Okay. And this is the voltage source inverter. These are the sensors, like voltage sensors and current sensors. Okay, then this is oscilloscope to record the waveforms. Then computer, then auxiliary DC power supplies used for the sensors and isolation circuits. Okay, these are the isolation circuits. This is the D space 1104. So this real-time controller I have used to implement the control system. Control system means MPPT and motor control. So this MPPT and motor controls are implemented using this D space 1104. You can use any real-time controllers like Opel RT, okay, then LabVIEW system or D space or any low-cost digital signal processor. Nowadays, very low-cost digital signal processors are available in 2000, 1500 or 3000 rupees. So that low-cost digital signal processors can also be used to execute these control logics. Then this is the BLDC motor. This BLDC motor is coupled through this DC generator actually, and this DC generator is feeding this resistive load bank. So when the speed of this BLDC motor is changed, output voltage of this DC generator will be changed, and accordingly the variable output voltage will be fed to this resistive load. So actually that power will be continuously changed based on the speed of BLDC motor. So this will actually characterize the function of a water pump. So these characteristics will be similar to the water pump. So you can see some of the results here. So this
Sir, can I ask one question in experimental?
Yes.
Sir, you have connected that BLDC motor DC generator with a resistive load. So how these characteristics match with the pumping application? Can you elaborate that?
Yes. So actually what happened, this is the resistive load. So we are actually feeding the variable voltage across this resistive load, because that voltage will be variable when the speed of initially what happens, we will change the power output of PV array. Means we will change the radiation level from 1000 watt per meter square to let's say 500 watt per meter square. So when the solar radiation is changed, power output of solar PV array will be changed. When the power is changed, means obviously BLDC motor speed will be changed, and this DC generator is coupled on this BLDC motor. So output of this DC generator will be changed. So output voltage is changed. So at the same time, since this is a pure resistive load, so voltage is changing, so current will also be changed. So ultimately power will be continuously being changed. In pump also what happens, characteristics of pump is what, if you talk about centrifugal pump, what happens, torque is proportional to square of his speed, right? Or we can say power is proportional to cube of his speed. Okay, power is proportional to cube of speed. And here, what happens? Power is proportional to the square of speed. So voltage is proportional to the current. Speed is proportional to voltage. Torque is proportional to current. Okay, we know. So voltage is variable since the speed is variable. Torque is variable means current is variable, right? So ultimately, this gives a similar difference is only in centrifugal pump. Power is proportional to cube of speed. In this hardware system, power is proportional to square of speed. That is the only difference. This is not exactly the centrifugal pump, but this is a variable power load, just like the centrifugal pump. Centrifugal pump is also the variable power load. This is also variable power load. So when our concept is working with this hardware system, that will obviously work with the centrifugal pump also, because this is implemented in variable power load. So this is somewhat same as the centrifugal pump also. Not exactly centrifugal pump, but somewhat similar to the centrifugal pump, because this is a laboratory prototype. This is not implemented in real field actually, right?
Yes, actually, my means, for example, if you are operating at 1000 watts per meter square, you have to make the load such that equivalent to 1000 watts per meter square.
Yes.
Again, if you want to change it 500, you have to change the load, or you need not to change any.
No. You don't need to change the load.
Yes, sir.
Voltage will be changed, then current will be automatically changed.
So means we are fixing the load at a full load.
We cannot say that we are fixing the load. Load is continuously changed, no? Because voltage is changed, current is also changed. So power is changed, means how the load is fixed.
Means in real time, for example, here we have to connect this home, we have to on the load now. That switches are there a red one.
Yes, we have to turn on this load, but then we will not change the load. That will be fixed.
Yes, sir.
But
that is my question.
power consumed by that load will be variable. That will not be fixed.
Yes, sir. Power consumed is variable, but whatever may be the on we are making
Yes,
this.
that will be same. That will be same.
That will fix. Okay, sir. Thank you, sir.
Hello, sir.
Yes.
Section, there is my two questions. One regarding that in grid interactive system,
Yes.
in two-stage system, we have the MPPT which will produce the duty ratio corresponding to the maximum power, and that boost converter will produce the output voltage. As well as here in the same slide, we have used the DC link voltage is sensed, passes to the low pass filter, and it is compared with the our reference or DC voltage.
Yes.
It is operated upon with the voltage regulator. So there are two controllers now. One is from the MPPT controller, which is producing the duty ratio. According to it, the output voltage of the boost converter will be produced, as well as this DC voltage controller, output controller.
Yes.
So how this DC voltage control is controlled?
In this slide only?
In the previous second one.
Here?
No, sir, other one.
This slide?
And there is a comparison of the DC voltage and the low pass filter is used, and it's compared with the reference DC voltage. In that PLL is used.
Okay. That grid interactive system.
Grid interactive system. Correct.
Here. Okay.
Here, exactly here.
So here you are saying that how this DC bus voltage is controlled.
One is the duty ratio is producing the output voltage for the boost converter.
Yes.
Right, and there is a in the right lower block, there is a comparison between reference DC voltage and the actual DC voltage.
Yes. So this.
So what is the function now?
So in this lower block, we are maintaining the DC bus voltage across this at the input of this three-phase VSI, and through the MPPT, we are adjusting the input voltage of boost converter. Through the MPPT, we are not controlling the output voltage of boost converter. We are controlling the input voltage of boost converter through the MPPT. And through this lower block, we are controlling the output voltage of boost converter.
Okay, but duty ratio will be generated according to the maximum power. And
Yes.
Depending upon the duty ratio, the boost converter output voltage will depend upon.
No. Input voltage will be variable. Output voltage will be always fixed. Output voltage.
Sir, but here between the input and output, as boost converter is placed, it means we are controlling both input and output voltage, no, sir. Then how it is
Yes.
possible actually?
Duty ratio is controlling the output voltage of the boost converter.
Because both are interlinked, no, sir.
Duty ratio means duty ratio of MPPT.
Yes, yes. Output of the MPPT controller is
Duty ratio. Am I audible?
Yes, sir.
Yes,
Yes, sir.
sir.
You are
Yes,
audible.
sir.
So actually, I got your question. Actually, okay. So
Depending upon the solar PV output voltage that is in
your
the
voice
boost
is not clear.
converter.
Actually,
Dear
And
participant, your voice is not
according to V upon 1
audible.
minus D. Yes, sir. Yes, sir. You are audible.
voice is not clear. Actually,
Ah.
okay. What is actually the if you talk about voltage gain of boost converter, output voltage divided by input voltage is 1 by 1 minus D. Okay, if you keep output voltage constant and when you change the duty cycle, input voltage will be changing, na? So input voltage that we want to change to get the maximum power. Let us fix the output voltage. We just want to change the input voltage. We don't want to change the output voltage. And by adjusting the duty cycle, that input voltage will be changed. That is actually desired to obtain the MPPT. Means through this duty cycle of MPPT, we are not controlling the output voltage. We are controlling the input voltage. Output voltage we are controlling through this lower block, which is grid side control.
Sir, in that case, can we operate without that voltage regulator also, as you mentioned in the lower block?
Without voltage control.
Without voltage regulator, where it is taking the difference of reference DC link voltage, VDC star and VDC.
Then how you will generate the reference current? That will be the question, no?
And also, sir, here we are using one low pass filter now. May I know what is the reason for that?
In this block?
Yes, sir, low pass filter, LPF. LPF below, sir. VDC, actual DC link voltage is passed through low pass filter, and then we are taking.
No, that is not low pass filter, that is single phase PLL.
Below one, sir, VDC, below voltage regulator. VDC is given to LPF, no, sir, LPF.
VDC.
So sensor DC link voltage is sensed and passes to the low pass filter to filter out some noises from it.
Okay. So that is used to filter some low frequency ripples, right?
But it may cause some delay, no, sir, like.
But that is a DC signal, na? There is no role of delay in DC signal.
Okay.
How to
So
select that
VDC?
frequency, sir?
That is DC voltage.
Yes, sir, but
So how this
why
VDC
we are
reference is
getting?
selected?
Yeah.
Sir, why we are getting the oscillation, sir, in the VDC actually?
Yes, actually, because you can see the output of three-phase voltage source inverter, that will be sinusoidal and frequency will be 50 Hertz. Okay. Accordingly, the input will have the frequency 6 times the fundamental frequency, means 6 times the 50 Hertz. That means 300 Hertz. So output this input voltage ripple frequency will be 300 Hertz, just like the three-phase rectifier, right? Ripple is 50 into 6, 300 Hertz. So that low frequency ripple should be actually suppressed. That ripple should not be allowed to, so that this our PI controller or voltage regulator can work properly. That voltage should be smooth.
How to choose the cutoff frequency of that LPF?
Yeah, that cutoff frequency you can choose based on the frequency. Like as I said, that the ripple frequency will be 6 times the fundamental frequency. 6 times fundamental frequency means 6 into 50. So that will be around 300 Hertz. So you can choose the cutoff frequency lower than the 300 Hertz, so that it can pass only the pure DC voltage. It should not pass the high frequency component. If you choose 50 Hertz or 10 Hertz, if you choose 10 Hertz, then that will be better. because we don't want to allow the high frequency ripples. So more than 10 Hz we don't want to allow. So that will give pure DC, and that is also a trade-off. When you select this cutoff frequency, then you have to change the parameters like KP and KI of your PI controller, because how we design the parameters like KP and KI. So this PI controller has these parameters. So when you add this low pass filter, that will also come into the picture when you design this KP and KI. Right. So in the design calculation of KP and KI, there will be an important role of this low pass filter cutoff frequency and order of this filter also. What order you are taking, whether it is first order filter or second order filter, that you have to take care in the calculation of KP and KI.
Sir, can you suggest any detailed document with respect to this designing and so that I can go through it?
Actually, the method is first to derive the transfer function of overall system. So you can see this lower block. So you can obviously derive the transfer function of this system. So by designing the transfer function of system and by studying the stability of that transfer function, we have to study the transfer function, stability of transfer function using some kind of Bode plot or root locus like that. Okay. So by analyzing the stability, we have to calculate the parameters, proportional gain and integral gain. That is actually the method. Otherwise, the alternate method is the hit and trial. You can choose any value of KP and KI, and you can monitor the voltage, whether it is being regulated or not. That is hit and trial method that you can use. Otherwise, good method is to go through the transfer function, derivation of transfer function, and analyzing that transfer function using Bode plot, through stability analysis like that. That is the proper method.
The transfer function is we have to consider between this ISP and input of PI controller or complete system like from
No,
PVLA to
you have to derive the transfer function of control loop only basically, but you have to see whether in this control loop your complete system is coming or not. If your complete system is coming into that actually plant transfer function. When you talk about plant transfer function, means your complete system is the plant. Right,
because sometimes we will consider the Bode plot for open loop transfer function without considering the plan. So that's why I'm getting a little bit confusion here.
No, without considering the plant, how you can derive the transfer function? Otherwise, it will be incomplete. Now you have to take this plant transfer function into account. Means total gain will be what? Gain of PI controller and gain of transfer plant transfer function. That will be the total gain.
So can you suggest any paper or anything if you
Okay,
have any idea?
I will send some material maybe later on. Okay.
Okay, sir. Please, sir. I will try to drop a mail to you, sir.
Yes. Okay, sure.
Thank you, sir. Thank you.
So I was showing these results. Okay. These results, you can see these results I have recorded from the solar PV simulator. So this shows PV curve and IV curve basically at different solar radiations. So first one is showing the PV curve and IV curve at 1000 watt per meter square. You can see this red one is the power versus voltage, and green one is the current versus voltage. And this scale shows the MPPT performance. This point shows the operating point. You can see this operating point is exactly at peak power point. So this shows the efficiency of MPPT, which is almost more than 99%, 99.8% for 1000 watt per meter square. And power, you can see power is 1450, which we have chosen 1450 watt because it is 1000 watt per meter square. Now for 200 watt per meter square, because now radiation level is just 20%. So power will be also reduced. Power will be 1/5. So power is 1/5, that is around 300 watt, less than 300 watt. You can see the next figure. And this scale shows the MPPT performance, which is in this case also it is more than 99%. So this shows the MPPT performance actually for single stage system for different radiation. So you can see for radiation 200 watt per meter square also the system is providing good MPPT performance. You can see these various results of solar PV side and motor side. You can see this is PV area power. First waveform is PV area power, PPV. Second is stator current of the BLDC motor. Third is speed of the BLDC motor. So if you talk about the starting, you can see this waveform, this screen. So during starting, I have controlled the stator current so that it is within the safe limit. It should not damage the stator winding. So starting current is properly controlled within the safe limit. You can see this is ISA, that is stator current of phase A. This is ISB, stator current of phase B. So you can see, as I said, in one phase current will enter, through the another phase current will exit. So when the current is entering, you can see current is positive, phase A. Current is leaving through phase B, so that's why current is negative here. And current C is 0, because at a time two phase will be conducting, because two switches will be turned on at a time. So only two phases will be energized. So third phase current will be 0. So IC is 0 here, right? So just for the understanding, you can see this is steady state results. Okay, these are the three stator currents, IA, IB, IC. Okay, and here you can see this is stator current. This is the switching pulse, okay, and this is the speed. So speed is 3000 RPM because we have designed everything we have designed considering the 1000 watt per meter square radiation. That is maximum radiation. Okay, so at a maximum radiation of 1000 watt per meter square, motor is running at rated speed, that is 3000 RPM, and this is the switching pulses. And if you see this frequency of the switching pulses, this will be 100 Hz, because the motor frequency is 100 Hz. Now these results are with the 200 watt per meter square radiation, right? Steady state performance at 200 watt per meter square. So at minimum radiation also this system is working properly. Only thing is that amount of water delivery will be reduced, because solar panel is providing less amount of power. So obviously the water delivery is reduced, but the system will work properly. Okay, power is reduced. You can see this is the power. So this is voltage, this is current, and this is duty cycle. So duty cycle is also reduced. Okay, when the radiation is reduced, duty cycle is also reduced, because duty cycle will be automatically adjusted based on the atmospheric condition. Okay, and these are the stator currents and switching pulses and the speed corresponding to 200 watt per meter square. So at 200 watt per meter square, speed is reduced around 1500 RPM. This is 1500 RPM speed. System is working. Now this is a dynamic condition when the solar radiation is increasing.
Sir, sorry to interrupt you. Sir, when the system is running, changing from 1000 to 200 watt per meter square, what is the change in the DC link voltage and MPP? So I think it is a single stage now.
Yes.
Yeah. Sir, can you show that DC link voltage variation from 1000 watt meter square to 200 watt meter square?
Yes. So yes, these results are for 1000 watt per meter square. Now you can see this voltage. This first one is the voltage. So this voltage is 270 volt, right? This is 270 volt. Now this is for 200 watt per meter. 200 watt per meter square. So now you see this voltage. This is not 270 volt. This voltage is around 210 or 220 volt. This voltage is reduced because this is single stage. So this voltage should be variable. So obviously this is varying 200 volt. Right?
Yes, sir. Thank you, sir.
Now this is dynamic condition. So solar radiation is varying from 600 watt per meter square to 900 watt per meter square. Okay, so radiation is increasing. So first you can see this. Since the radiation is increasing, output power is also increasing. Okay, so this is PV output power. This is increasing. So since the output power is increasing, obviously speed and current of motor will increase. So current of motor is increased. Similarly, the speed of the motor is increased. Now these are the three-phase currents: ISA, ISB, ISC. Now the reverse case is that radiation is decreasing from 900 watt per meter square to 600 watt per meter square. So power will decrease. You can see power is decreasing. This is PV power. PV power is decreasing. So stator current is also decreasing and speed is also decreasing. So these are three currents, IA, IB, IC.
Sir, in this case, sir, one more query, sir. Sir, when the irradiation is changing, as we can observe that PV power is changing like linearly, it is
Yes.
slowly decreasing.
Yes,
Sir, how can we have that kind of variation with the help of programmable AC source? I mean, what type of settings we have to do in that? Because as it is, as we are not using physical solar panels,
Yes.
will it take place instantaneously or how it depends?
So in solar simulator, what we do, we just put the values of radiation level. We put 1000, then system is running as 1000, then suddenly we will put 500 watt per meter square. We will just fill the value and press enter. So when we change the solar radiation, because motor has some inertia, it will take some time to reduce the speed. So you can see power is slowly reducing because we have to obtain the MPPT also. Okay, so this time which is taken to reduce the power is this is due to the inertia of motor. But we are reducing the solar radiation immediately. We just put 500 and press enter immediately. We are not changing the radiation slowly. We are changing immediately. Suddenly we are changing.
In that case, sir, in that case, that simulator, what we are using, it can change instantaneously, sir, that power.
Yes, yes, yes. This is just a programmable power supply. It will change instantaneously.
Yes, sir, actually, that is my doubt, sir. It can change the power instantaneously, but in the literature, I can observe it is changing.
No, it can change the radiation immediately. It cannot change the power. You can change. You can see power is changing slowly. It can just change the radiation, but power will be changed slowly.
Okay.
From this result, we can see the power is changing slowly. Power is reducing slowly. But we are changing the radiation in step. Okay, we are not changing the radiation like a RAM signal. We are changing like step signal.
It means this slope depends on what parameters, sir? Like it depends on the PV simulator settings or any load we are using.
It depends on the inertia of motor. It also depends on the step size of your MPPT technique.
Okay, okay.
Right.
Thank you.
So accordingly, these currents are also decreasing. So coming to the various applications, what are the possible applications of this solar water pumping system with this BLDC motor? This can be used everywhere, wherever the water delivery is required actually. In our homes.
Sir, how you control that starting current? By matching the inertia time constant with the step size of the
starting current we are controlling by controlling the duty cycle. As I said that we can start increasing the duty cycle from 0 value. Then
slowly you are achieving the duty cycle which will give you MPPT.
Yes.
So that is perturbation size, that depends on the perturbation size.
Yes.
Step size.
Step size.
Okay.
So these are the various applications, like it can be used for irrigation. Okay, it can be used for drinking water supply in the households. It can be used in swimming pool, fish ponds, fountains, and water supplies in industries, and anywhere wherever the water supply is required, we can use this. These are the immediate application. In future, we can use for water supply in trains, in airlines, in defense sectors. Okay, and this is again which I have already shown, the grid interactive solar PV powered BLDC motor driven water pumping system. In a standalone system, only drawback is what? When we have excess solar power generation, and when sometimes we may not need water pumping. Okay, water pumping may not need 24 hours. And when we don't need water pumping, then our solar power will be wasted. There will be no use. So that will not be properly utilized. So to utilize properly, what we can do is we can connect that solar PV array into the grid, and when the water pumping is not required, in that duration we can feed the power into the grid. That will be the full utilization of solar PV array. One more thing is that sometimes we may need more water delivery. We may need continuous water delivery. We don't want to compromise with the amount of water delivery. But in a standalone system, when the PV power is reduced, water delivery is reduced. So that is difficult to achieve continuous water delivery So what we can do when we connect with the grid, we can draw some power from the grid to get the maximum amount of water delivery. So during bad weather condition or during morning or during evening, motor will take some power from the PV array and some power from the solar from the grid. So there will be a contribution of PV array and grid to run the motor at full speed and full torque. So that will be the actually some benefits of connecting the solar PV array with the utility grid. In the system, I have used a single phase grid. Obviously, for more capacity, we can use 3-phase grid also. So the single phase grid is used here, and this solar PV array is interfaced with the single phase grid. So this is a 2-stage system. We can develop single stage system also. So here, when this BLDC motor is not used, means when this water pumping is not required, the PV array power will be transferred to the single phase grid. And when the solar PV power is not available, let's say during night, solar PV power is not available, at that time, this motor will draw power from the single phase grid, so that water pumping is continuously achieved. That is the logic only. And when we interface this solar PV array with the grid, we have to take care of the power quality. That is important. We have to take care of the total harmonic distortion of the current. We have to take care of the power factor of the current. So this control, this simple control, this is simply unit vector template based control. This is used to maintain the power quality at the grid side. You can see some waveforms here. Here, these are the this is the source current. This is the source voltage. So power factor also we can see in total harmonic distortion. This is, you can see, 2.9% total harmonic distortion of the source current. This is the dynamic condition. So SPV array and grid feeding pump to SPV array grading pin means initially SPV array, solar PV array and grid both are used to feed the pump, and then after some time only SPV array is feeding the pump. Means let's say grid has been failed, grid voltage is 0. Okay, you can see this last waveform. At this point, grid voltage is grid current is 0, means no power is taken from the grid. Grid is failed. So at that time, all the power will be taken from the solar PV array. So what happens? The phase of the current will be changed. You can see initially the current is in phase with the voltage. Okay, source current is in phase with the voltage, but after some time you can see the source current is 180 degree out of phase with the voltage, because direction of power flow is now reversed. Okay, direction of power flow is reversed. Now power is being fed to the grid. So direction of power flow is reversed, means direction of current is also reversed. So that's why this current is 180 degree out of phase with the voltage. So in conclusion, solar water pumping is obviously an interesting research area wherein a low cost, efficient and reliable solution is always desired. Okay, Government of India is continuously promoting the use of solar water pumps, but still our Indian farmers are not adopting it. What may be the reason? That is the question. So the reason is, the first reason is still the cost of installation is somewhat higher. And second reason is Government of India is providing subsidy on the electricity bill. That is the reason. When the Government of India will remove the subsidy on the electricity bill, then farmers will forcefully adopt the solar PV system. That is the mistake of Government of India. Mistake of Government of India is what? It is government is providing subsidy on the electricity bill. It is government is not charging any bill from the farmers for the irrigation. So farmers are enjoying. They are saying that we are not paying any electricity bill. So why we will install solar PV panel? So they are enjoying. When government will put some electricity charge on the irrigation, then farmers will be forced to install the solar PV. So as an engineer, what we can do is we can give some solution, means we can give low cost solution, we can give efficient solution, we can give reliable solution to the middle class farmers of the India, so that they can easily adopt this solar water pumping system. The proposed approach is justified by this experimental analysis. Then we have eliminated the Hall effect position sensors, and that makes the system reliable for the submersible water pumping especially. So basically for submersible water pumping, we should not use Hall effect position sensor because these are not reliable. At last, DC-DC converter-less that is single stage approach with position sensorless control of BLDC motor gives the best solution for solar water pumping. So when we eliminate DC-DC converter, that can reduce the cost of the system, that can also reduce the size of the system. So these are the advantages of this topology. Okay, any other question? Then we can discuss.
Hello, sir.
Yes.
Hello, sir.
Okay, please.
Sir, I want to, you have implemented to the D space 110 for controller.
Yes.
But, so my question is, how we decide the sampling time to execute this programming? Because a lot of time we build the program but while executing it, while dumping it, the problem comes, sir.
So that actually that sampling time is actually it depends on the switching frequency of your power electronics converter. So if your switching frequency is 10 kilowatt, then your sampling frequency should be more than 10 kilowatts. It should not be 10 kilowatt. Then only it will be properly implemented. So that should be related with the switching frequency of your converter or inverter.
Okay. And what about the other component, that controller, that is the outer controller, inner controller there? What should be that speed? Should be different or the same only? It should execute at the same sampling time.
Can you repeat?
There are the inside the controller, we have the outside controller, inside controller, right? Current controller,
Yes.
reference generator controllers. So their execution time is same, sampling time is same again, this controller?
You can put different also, but that sampling time should be more than the sampling time which you are putting for the your processor.
Overall system.
Yeah. Means if you are taking 1 microfarad sampling time, then sampling time of your controller should be more than 1 microsecond.
Second. Okay. Fine. Thank you very much. Thank you.
Sir, may I audible? Am I audible?
Yes.
Sir, your lecture was very quite informative and it was very interesting topic. It is very interesting, right? So you have given a detailed description of control strategies and all that. But my question is somewhat different. I may be wrong also. In power circuit, when we are talking about BLDC motor and your inverter circuit, so over there machine dynamics come into the picture. Fine. So what reference frame we have chosen for the studying the dynamics of the machine?
Reference frame means?
Reference frame means, sir, whether it is synchronously rotating reference frame or it is rotor reference frame or stator reference frame, because you have talked a good topic on control circuitry, but there is also power circuitry is there. Fine.
Yes.
So we have to choose the reference frame first, because for implementation of PLL, we have to implement we have to find out theta, and theta has to be synchronized with the system. So what reference frame you have chosen? This is my question.
So I have taken PLL for the grid side control, actually, not for the motor side control. And
no, PLL is fine, sir. The PLL is for phase lock loop, no?
Yes.
You have to actually that is actually capturing, but theta has to be calculated on the basis of reference frame theory. So if you can elaborate, then it will be fine. Otherwise, I can understand it's a totally different topic.
But theta means theta. You are talking about the output of PLL, right?
Yeah.
So that angle is actually the angle of voltage, phase voltage.
No, that is fine. But see, the thing is that whenever you're talking about machine and pumping system, right? So if what I understand that if you are putting it to synchronous system, fine. Because I think you have been used rotor reference frame because you're using positioning and Hall sensors. So the reference frame has to be rotor reference frame. This is my understanding. I may be wrong also. So am I able to clear you? If you are going on to the slide number where you have applied PLL and all that will be more clear.
Here?
No, PLL. Yeah, on this side. See what is there, you are getting VS, right?
Yes.
And see, basically the problem is that from PV and over here after C, we are connecting it to grid. Fine.
Yes.
And if we are not choosing the proper reference frame, it will be difficult for because synchronization is the major problem. So the power generated from the PV is stationary, whereas the power from the single phase grid is varying. So if there will be the proper reference frame will not be chosen, then there will be a short circuit, dead short circuit will be there, and that may burn the system. So to the best of my knowledge, the power circuit must have some reference frame.
Power circuit that includes motor along with the power.
Motor, inverter, and all that.
Yes,
Fine.
along with power converter.
Yeah.
So your question is that what reference frame I have chosen, like that?
Yeah. Because see, whenever you are taking the actual system, otherwise if you are simulated, then it's fine. But when we are implementing it onto the actual system, so that is a prime requirement.
So in control, actually, since this is not a closed loop control, this is just an open loop control. We are not using any closed loop control here. So what I am doing is I am leaving the BLDC motor to rotate at whatever power it is getting from the PV array.
No,
So
sir, the question is not of this particular part, that whether it is a closed loop or open loop, but because we have to connect it to the grid. Fine. So if it is not synchronized, and the stationary power plant that is composed of PV has to be connect onto the single phase grid. If it is not properly synchronized, there will be a dead short circuit. Anyway, this is a totally different subject because reference frame theory is very important to understand. But anyway, it's fine. Otherwise, it's a good presentation. So I think, to the best of my knowledge, I want to just counter check that whether am I right or wrong. To the best of my knowledge, this must be rotor reference frame, because you are using BLDC.
Sir, can I hear him?
Will be there.
Hello. Yes. Hello.
Yeah. You are audible, sir.
Sir, one thing here. Hello.
Yes.
Actually, sir, the sir is asking regard of the synchronization, but we are connecting grid with the DC link. We have the single phase VSC. So I think synchronization is not required, because we already connected the grid with our connection with the DC link.
No. Whosoever is talking, that is fine. See, basically what is there?
Hello, sir. Sorry for the disturbance, but we have to wind up the session now, because we have another session at 2 p.m.
Right. Okay.
So if participants will.
Right. Thank you.
Yes, sir. You can contact to sir by through mail also.
Okay. Definitely.
Okay, actually we can discuss later on for
Don't take it wrong, because we have to.
I can understand.
Yes, sir.
Please.
Yes. Okay, so.
Prashant sir, if you don't mind, I have a small doubt, sir.
Yeah.
It may take only 30 seconds.
Yes.
Sir, in this case, suppose if the boost converter is not available, and let's say at STC condition, PV voltage is 270 volt. So DC link voltage is also 270. When the irradiation is decreased to 200 watt per meter square, as you have shown in the experimental result, DC link voltage is reduced from 270 to maybe around like 220 or 240 something. So, but anyhow, at the other side, we are using voltage regulator here with the help of PI. Why can't it be voltage is maintained at 270 volts?
That VDC.
Yes, sir, VDC.
So
if the boost converter is not there, in that case.
So if you maintain that at 270 volt, then it will not be possible to achieve MPPT. Because you are fixing the voltage, na? For the
Yes, sir,
for achieving the MPPT, voltage should be variable.
yes, in that case, what function this voltage regulator is doing? That's what my doubts are actually. Because
in
one
that
side
case,
we are.
In that case, that control system should be slightly changed. That same control system will not be used for single stage actually.
In the single stage, this voltage regulator is present or absent, sir?
That will be present.
In that case, always the DC link voltage has to be maintained constant, sir, irrespective of irradiance.
In grid connection mode.
Yes, sir.
No, that can be adaptive DC link voltage also. That is not mandatory to maintain. In grid condition also, that voltage may be variable.
Okay, sir. It's a very nice presentation, sir. You have taken very long time for 3 hours. Thank you for answering all the questions with patience, sir, in between also. Thank you, organizers also. Thank you.
Hello. Hello. Yes, sir.
Hello.
Yes, sir. So thank you, Rajan sir, for giving a wonderful session. We have extended more than our time also because the participants were so much engaging and you have cleared all the doubts, everything very nicely. And I would like to thank for the nice presentation and taking all the questions.
Okay, sir. Thank you. Thank you for inviting me in this lecture.
Thank you, sir. Yes. Participants, we will meet at 2 p.m. exactly. Please come back to at 2 p.m. exactly because second session will start exactly at 2 p.m.
Okay.
Sir, can I get your mail in your website so that?
Yes.
Yeah. Okay. Okay, sir. I will drop a mail.
Okay. Thank you.
Thank you. Thank you, sir.